In the name of God, the compassionate, the merciful, Engineering Plasticity, Chapter 1, Introduction, Part 8. What kinds of deformations are there? A stress-strain diagram in compression. Now we have talked about tensile test and a bit about compression test. But here we want to use compression test to see how the deformation is occurring. Okay, if you look at a simple compression test of a cylindrical specimen, supposing this is a cylindrical specimen, and we are compressing in that direction, that is the initial position and that is the final position. Okay, as we compress the cylinder, the diameter of the cylinder increases and its cross-sectional area increases. What happens to the material flow? As you can see here, as we press, because this side of the cylinder is in contact with the press platen. Okay, so there is a force all over the place, downwards and here upwards. So what happens? The material wants to flow out because, as you can see, it has to increase in that way. So as the material wants to flow out against the surface of the press, there will be a frictional force like that, just opposite to the flow of the material. And this is what happens at the bottom and also at the top. So we can say that the material flow is hindered by the frictional forces. If we lubricate this surface, obviously frictional forces are reduced. If we do not lubricate, we will have high frictional forces. So how much we lubricate is an important factor in this metal forming process. Now we have this homogeneous compression, which is like this. I mean, the deformation everywhere is homogeneous. That is to say that the deformation, as we increase the load, does not change from place to place. Everywhere is the same. Okay. To illustrate further, we check with the non-homogeneous compression. In non-homogeneous compression, barreling occurs. Barreling is this, it's like a barrel. As you can see, it means that the material flow at the top is hindered and the material flow at the middle of the cylinder is easier. That means that it's due to this frictional force. Because we have this frictional force here, it prevents the material to flow out. But in here we don't have those frictional forces, so it will flow more, and from here to there is a nonlinear relationship, so that we get this curved surface. Obviously, barreling could be avoided by proper lubrication, like PTFE at the flat surfaces there. If we put PTFE here and there, then between the platen and the cylinder, then material flow will be easier, and this barreling will be diminished. Okay, it becomes minimum. In this slide, we are seeing the same compression test, but different phenomena has happened. What's happened here? Bollarding is what's happening in here. What is bollarding? As you can see, the compression test in here causes the material flow on the top to go further than the material flow in the middle. What's happening here? Here we have lubricated the surfaces very well, perfectly lubricated, and therefore it allows the material flow to go further. But why at the middle hasn't gone as much as that, as the top? It's because this is a free surface. This is a free surface, but the atoms and crystals in here, they have neighboring atoms, neighboring crystals. They are surrounded by all these crystals all over the place, and therefore there is a barrier to their movement. But here, because we have a free surface, on the free surface we have no barrier to the flow of material if it is lubricated very well. Therefore the material flow in here will be more difficult than in here, and we get this phenomena which is called bollarding. To further illustrate the homogeneous and non-homogeneous deformation, the nature of the homogeneous deformation, I have put this picture from an extrusion process. Now then, this is the initial billet which we have put in the container and have pushed it forward through the die, and it has decreased its cross-sectional area as you can see here and there. Obviously here the die angle is smaller than here. It's two kinds of dies. But what we are interested here is this grid deformation. We call these grids. As you can see, we have made a grid on the cylinder, and we are looking at it, how it is deformed. Now this is a perfect deformation. It's a homogeneous deformation. It means that these rectangles that we have marked on the cylinder, as they go through the die and deform, as you can see, they preserve their shape. They are also here. We can see it's a rectangle. It has not changed. Okay, it has not been distorted. That's the homogeneous deformation. Okay, so the deformation is homogeneous if the grid deformation remains ideally the same. I mean, the rectangle remains rectangle. But if this rectangle was distorted in any way, we would say that it's not a homogeneous deformation. Of course, we don't have homogeneous deformation in practice. Sometimes we use it to model a problem in a simpler way, in an ideal way, and to solve the problem. But homogeneous deformation really does not exist. As you can see, this is a real extrusion process. We have cut the cylinder in halves and we have graded it like this. We have these grids in here beforehand, and what we do is that we half the cylinder, and then on one half we put these grids and glue the two halves together and extrude it, and after the extrusion we open up the halves and we see this grid deformation. As you can see here, these lines are straight, but here they have become distorted and different shapes, and so we call this non-homogeneous deformation. I have some more examples, for instance, for the extrusion as well. Different patterns depending on the material and the die and everything, the condition of deformation. We could have different patterns of deformation. All of these are non-homogeneous, as you can see. You see these rectangles here, they have changed quite appreciably, especially in here, and they have been distorted completely. So this is called non-homogeneous deformation. Now I want to look at some behavior of the material and some empirical equations. Okay, empirical equations. What are empirical equations? Now we are familiar with the term of equation. We have some theoretical equations which we derive based on some assumptions. We may have experiments. We do experiments like tensile test, and we have quite a few points in here, okay, for the tensile test. Now and we draw a curve on those data, and we say this is the tensile test results. Now for these curves, we can fit, for this data in fact, we can fit a curve on them like that. You see, this is a Ludwig equation. It's a curve fitting. We have some data, we fit the curve on it. And this is called empirical equation. In fact, this is an equation but based on experimental evidence. Okay. Now this Ludwig equation has two constants, c and n. Sigma equal to c epsilon to the power of n. This n is called the strain hardening component, right? So we have here sigma over c and epsilon. We have plotted it. We have given some values to epsilon, and we got we get a value for sigma if we have numbers for this, for c and n. As you can see, we have changed n from 0 to 1 to see how it behaves, okay, for different materials. One material this curve may fit for one material, the other one may fit for another material. As you can see in here, for n equal to 0, we have no strain hardening, okay, no strain hardening. And for n equal to 1 also is a straight line like elastic behavior, right? But for the rest of between 0 and 1, we have some curves which shows the plastic behavior, okay? Plastic behavior. If epsilon is 0, sigma is 0. So it starts from 0. It could be used for aluminium and those kinds of materials. We have many empirical equations like this which we use in our work and tackling the problems and analyzing different problems. I will show you some of these in here. As you can see, this is another one, y multiplied by 1 plus m epsilon to the power of n. Okay, these m, n, and y are constants. Y could be sigma y, in fact, which is the yield stress. Is constant anyway. I have kept m constant equal to 0.6 and changed the exponent n, and you can see how this changes. Obviously it starts from here because it's just for the plastic part of the curve. Swift equation is another one which is very much used. Voss equation also is the famous one. As you can see, all of these start from some points in here. It means that they just simulate the behavior, the plastic behavior of the material, and not the elastic. We don't have the elastic parts in here. We could add the elastic behavior to these equations as well, like here. Okay, this is modified Ludwig equation. It has the elastic part and then the plastic part. E epsilon y, E epsilon to the power of n divided by y to the power of n, and we can have this for defining material behavior. Okay, another one is the Romberg-Osgood equation. As you can see, I have taken this constant 3/7 and I have changed m to get different behavior for this equation. Now this is another one, Prager equation. It's a very good one because it gives from elastic to plastic. Now for rate sensitive materials, what is a rate sensitive material? Rate sensitive materials are those materials who are sensitive to the speed of loading, because as we mentioned before, strain rate shows the speed of loading. Therefore epsilon dot is the strain rate, and rate sensitive materials are sensitive to this strain rate. Okay, it means that if the strain rate changes a bit, they show very large responses to that. So that means they are sensitive. Okay, now for sensitive materials we use this equation. In fact, in previous equations, if you noticed, we just have epsilon and sigma, but here we have added epsilon dot as well to define the material more precisely. These are just for sensitive, rate sensitive materials, because if the material is not rate sensitive, it means that its response to the strain rate is not very large, is small, and so it's not sensitive to the rate, so we don't need to consider this, which for most materials at normal conditions we don't use this. Okay, this is another one. And here again I have changed in here, of course, different properties, N, M, and so on. Okay, I have, as you can see, I have used for different rates epsilon dot 10 to minus 3, 10 to minus 1, etc. Now here I have Johnson-Cook equation. You may have used this equation before. This is a very famous equation which includes everything. It includes epsilon, includes epsilon dot, and includes temperature. Okay, in previous equations we didn't have a temperature, so the effect of temperature was removed, but here we have all of these in a function like that. And this is an example for aluminum 2000 series, heat treated T3, and strain rate is 0.02. Okay, experimental data for different temperatures. Right now, this line is Johnson-Cook model, and these are the experimental values. Okay, these are the experimental values, as you can see. So we have compared Johnson-Cook with the experimental values. For instance, here for the 350 degree C, you can see this Johnson-Cook gives very good results. For 150 also it gives good results, but for 20 degree it doesn't, because you see the real data drops, but the Johnson-Cook continues like that, which is not correct. Okay, so this equation predicts the behavior of material at high temperatures, relatively high temperatures, and that's very helpful.